Okay, I'll let you all assemble. Okay, my name's Andrew Faraday. I am a web developer during the day, and I once, long ago, did a degree in popular music and sonic arts. And so I can't help but make music with computers, basically. And what I've got planned for you today is a lightning tour of something called Pure Data. Now what that is a real-time graphic programming language, all open source. And don't switch off too much if you're just interested in your web audio, because the metaphor you need to learn for web audio is that you create audio objects that are one little box that does one little job, you then connect them up, and then you interact with them via your code. And that's actually what you're going to see on screen. That's how Pure Data code fits together. So without telling you too much, I'm just going to get on and show you. First things first, actually I'm going to have to shrink my font ever so slightly. Right, first things first, this is an object. It's a little function that sits there in real time and does what it does. The tilde at the end of incidentally just means it's dealing with audio. And you notice that's an audio multiply, which means it's basically the same as the gain node in web audio, and what it's doing is it deals with audio. Digital audio is a stream of numbers, as we just heard, as Chris Lowe's sort of conveniently described for us. And what happens when you multiply a number by 1, of course, is it stays exactly the same. And when you multiply that same number by 0, you get 0, which responds to, sort of results in no movement to your speaker, results in no sound. So multiplying anything by something between 1 and 0 is going to reduce the volume. So that's all I'm doing there. It's just taking the volume down to a tenth. I may have to make it louder by creating an oscillator, giving it a frequency. So when I connect this up, we should all hear a tone, and I'm going to stop my test tone. There we go. And first thing you'll notice is that tone will drive you completely nuts if we don't change it. So the first thing we need to do is give it an on-off switch. I'm going to use another multiply and a toggle, which in Pure Data is just, it's a switch that describes lots of binary things: on, off, start, stop, good and evil, true and false, as 0 and 1. So when I click this box, it will then multiply that tone by 1, and we'll hear it start and stop. But also, if I do this a bit quickly, if you just listen, you also get a nasty little click as that happens. And all that means is your computer's working a bit too quickly, going from wherever it is to 0, and we're hearing the speaker scrabble to keep up. So all I'm going to do is a little bit of smoothing. Now, with this line object, which is just a linear argument, and what this will do is it'll take that first value, $1, and take 1,000 milliseconds to get to its speed. So we'll hear this fade in over a second and fade out. Well, of course, if I bring that down to 10 milliseconds, it's a bit too quick for us to actually hear with human ears, but you don't hear the click as that goes on and off. Right, the next thing we probably want to control, because this is my demo of how to make a musical instrument in 5 minutes. So the next thing we probably want to control is the pitch. And so I'm just feeding a number into the oscillator here. I turn it on. I've suddenly got a lot more control of what's going on. But and this is actually a really simple musical instrument, because we've got a sound, we can start it and stop it, and we can control the pitch. But it's not a very useful one. If nothing else, we can't start and stop it and change the pitch at the same time. So what I'm going to do is use an interface over here, something called mouse state. Now, there's quite a lot of things in Pure Data, and if you want to work out what one of them is, you can always right-click, click Help. This will probably come in a bit too small for you to see, but that's actually a working patch to show you what mouse state does and how to use it. So what that's taught me is I expect 2 numbers and a toggle. And when I feed it a message called poll, it will start to feed me information on my mouse right now. And what you'll see there is my current mouse position. If I go up to, off the end, 1359, or down to 767, and of course I'm in the top left corner, that's 0. So these are values I can use also. You see when I click my mouse, that toggle turns on. So I could just connect that toggle directly to that toggle, and I've got control of whether it goes on or off, but that gets really very messy very fast. You get wires crossing, which looks very difficult to read. So what I'm going to use is an object called send, shortened to S, button, and this is basically just a variable in real time. So what goes into the send comes out to receive, of the same name, and I've got that control on and off. Now the X position of my mouse from left to right is up to 1359. That's quite a good range to be playing with anyway, so all I'm going to do is send my X position over to my pitch. And what we'll get is a very simple musical instrument controlled by the position of my mouse on the screen. Okay, it's not very precise, and I'm not very accomplished at playing the pure data mouseophone, but the point is, it's all there. And normally, I haven't been checking my timings, normally that takes around 4 minutes to do. So I'm just going to show you a very simple effect down here on my volume line. So I'm going to use an object called del write. All it does is it writes a buffer, named D1. I'm going to give it 1000 milliseconds. Just saves that second worth of sound. It's got a partner object called del read. Same name. And when I connect that up, what we're going to hear is the same sort of musical sound, but repeating a second later. And this is used for the sort of classic echo effects, but of course we know echoes don't come back at exactly the same volume that they went in. So I'm going to reduce the volume as it enters my delay line by a half. And so we'll get that again, but it'll be a little bit quieter. And of course that sounds unnatural as an echo because it echoes once. So next thing we're going to do is send, again with a tilde for an audio object, call that feedback, FB, and feed that back into the top of my delay line. You can probably tell what's going to happen at this stage. We'll hear that sound again, and it'll repeat and repeat till it eventually fades into obscurity. And just for the last bit of control, I'm going to use my Y position, so from 0 to 767. I'm going to be playing with volume, and that's a ridiculously high level for volume, so all I'm going to do is use an object. It used to be called scale, used to be called range rather, but somebody's decided to shorten it to maxlib/scale. And basically it takes the values of the range of numbers that are going to go into it, and the range of numbers that's going to go out. So if I connect a number just below that, you'll notice at the bottom of the screen that's 1, at the top it's 0. Send that to Y. I'm going to do my volume smoothing thing just again. It's quite nice to actually do this and get the instrument as I go. So that's just going to be the amount of feedback, and now I've got a bit more control because I've moved the mouse to the bottom of the screen. That will of course never fade out. And if I move it to the top, we start to lose that. And so that's actually quite a unique, expressive instrument. And again, not been checking my timings in about 5 minutes. So that's the first thing I had to show you. The second is another sort of party piece with pure data, and it goes like this. There's a... You wanted me to make the next one with that on, didn't you? Okay, right. I'm going to have to move the font up on this now, but never mind. Right. Basically, it's a little known fact of the English language that synthesis is the opposite of analysis. And what that means is when we analyse something, we take it apart, understand what the component parts are, how they fit together and how they interact with each other. So when we then synthesise something, we use those same components and those same principles putting it together, and we make it again. And so this can be applied to music. So if you look at music in the Western world, certainly, it tends to have at least 4 elements that I can recognise. It tends to have rhythm, which logically is an amount of time that repeats, and then is divided by integer values. So you have factors of that amount of time, and then sound events are arranged within them. And when you hear that, it tends to be rhythm. So I'm going to start with a very simple system, an object called click. Incidentally, I didn't describe earlier, but you may well know DAC is digital to analog converter. And that takes a message, called a bang. And all that happens is when that bang appears, we hear a little click. Now, I know that's not very impressive. Your mouse probably clicks anyway. But, of course, I might not want to do that. I might want to automate this process. So I'm going to use something called Metro. And all that is it's going to output that same bang activation message once every second. So if I start this, It's like a clock ticking, and I can actually change this dynamically. That's twice as much. And when I get down to sort of 30 milliseconds or so, that runs into one sort of singular event. So what I'm going to do, of course I might not want to sit here picking numbers all day. I'm going to have a random. Random 100, by the way, means values from 0 to 99. Don't let that worry you too much. And another metro up here. And all this is going to do is every quarter of a second, it's going to pick another regularity for that second metronome and second click. And that's a sort of very simple sort of music algorithm going on there. But what I'm going to do is to just sort of modify that slightly. So I'm going to write a table or array. It's basically a list of numbers in pure data called lengths, which I keep misspelling at the moment. So give it a message that says lengths from index 0, 1000, and dividing by integers, remember, so 250, 112.5. And I'm going to move that random down to 4, which means I'll get values from 0 to 3. I'm going to have a tab read, which reads a table. I think you'll probably work that one out. So it'll take, now every quarter of a second, or move it up to a second, it's going to choose whether to click once, twice, 4, or 8 times. And if I've done this right, what we're going to hear is it's something a bit like a sort of drummer's exercise, a sort of little rhythmic exercise. And that is, in logical computer terms, rhythm. And it sort of sounds like some. So the next thing I said we tend to get in music in the Western world is pitch. No, I don't want to close it. Right. So, yeah, I know, right? It seems to have lost my position as well and just be doing the same tone. So I'm going to cut that. Sorry. Right. So just the same again. I've got an oscillator, DAC, and I'm reducing the volume as it goes into it. Incidentally, my screen's somehow got more pixels than the one up there, so I might lose things off the edge a little bit. Don't worry too much about that. So, I know I can get a metro. I know I can choose a random number. And I know that I can then control the pitch of my oscillator. And what we're going to hear now is every quarter of a second, it's going to choose a random number from 1 to 1000 and play that pitch. And it will drive you completely nuts. So again, all I'm going to do is multiply line $1.10 and a toggle, and I'm just going to put a receive in there called start, so I can start and stop these all at once. Which of course then I can feed up there and into my sort of melody generator thing. So S start and a toggle. By the way, this is very sloppy code. I'm doing it on the fly. So what we'll hear now is I can start that sound and that melody generation at the same time, and I can set it to also do the little drummer's exercise on top of it. And so in a very simple way, we've now got rhythm, we've got pitch, and we've got melody, because we've got one tone after another. The melody itself doesn't have very much rhythm, so all I'm going to do is I'm going to cut that part there and replace it with the same rhythm generator that I'm using for my little drum. So and it's doing the same thing, but it's still not a very sort of sophisticated system. It's choosing random pitches that don't really fit together. So I'm just going to give it an array called scale, which is going to be a set of notes that we in the Western world tend to sort of agree are roughly nice enough together. And so again, sending to scale from index 0, 0, 2, 4, 5, 7, 9, 11 and 12. You may recognise that as the tone relationships in a major scale. And so I've moved that down to the size of my scale array. I'm going to do tab read scale, and because I'm using MIDI notes here, which are just each integer number is a semitone value, and that always goes from 0 to 127. So plus 60 to bring us to the middle of the MIDI range, and a conversion object MIDI to frequency. And so now what we're going to guess, it's going to pick a set of sort of notes that we are sort of used to hearing together. You notice that sounds sort of quite nice and consonant, so we've got a sort of Western idea of what pitches are good. We have rhythm, we have pitch, and melody. So the only thing that's really left is harmony. That was easy. Actually, no, I've just realised I'm using my laptop speakers. I'll keep it in both sides. So now what will happen is I'll have two rhythm generators feeding two melody generators feeding two synthesizers, and what we will get will have all those elements of music I mentioned earlier. Also, incidentally, because they're not doing the same rhythm, we've also got counterpoint as a free gift in this one. And that is how we can use some very simple analysis of music, recreate it with code, and make music completely from scratch. And that's the last thing I had to show you. Bear in mind, all of this can be done with the Web Audio API. I'm just throwing around all the same sort of ideas and functions, and yeah, you could do this yourself. You absolutely could. Thank you very much. Any questions? Yes.
Yeah, my name is Martin.
Hi, I'm Andrew.
Yeah, hi. This is really cool. I've done a little bit of PD before. Really enjoyed it, but this is like actually way more advanced than anything I've ever made. It's a lot of fun. But so I didn't know you could actually get this to run in the web. Is that a feature? Or?
Okay, I may have described that badly. There's lots of projects which try and put pure data in websites, and so far I haven't seen one that works very well. If you use the Web Audio API, it has gain nodes, which are the same as that multiply, has oscillators, has the outputs, has random number generator. Basically, everything you've seen here can be done with the Web Audio API.
But there's no way to like export my PD hash to the web.
No. Somebody's probably trying it, but they're probably failing. And that's my experience of PD in the web. That's
Thanks.
no problems. Any more? Thank you very much. Oh no, one over the corner.
We'd like to hear you beatbox.
Yeah, sorry, this was an earlier conversation. Let's see if I can jam with this a bit. Nope. That was awful. That was better than my talk. I'm impressed. Thank you very much. I'm going to run away now.